We're going to look at a momentum problem today. I'm holding this big ball, like so. I'm not moving. The ball is not moving. The momentum of me plus the ball is equal to 0. If I take the ball and I throw it really hard in that direction, the ball is moving to the left. So it's acquired a momentum to the left. So in principle, I should acquire momentum to the right, because the sum of the momentum of the ball plus the momentum of me should be equal to 0. Now, that's going to be hard to demonstrate in the studio because the ball is actually not that heavy and I can't throw it that fast. But there are places in sports where it actually shows up enough that we can make a measurable difference. Let's take a look at one right now. This is a video that I made of a student in my class who just happened to be a softball pitcher. And I said, I want you to come out and give us a really, really fast pitch, and we're going to videotape you as you do it. So Chelsea is running forward, and of course she runs forward so that she has a little bit of forward velocity, and that will, of course, add to the velocity of the ball with respect to the ground before she even throws it. So this is a plus. Chelsea's moving forward. She takes the ball, swivels it around, and then throws it at a very, very high speed. Now, we analyzed the video, and we discovered that she threw the ball at a speed of about 25 meters per second. Right before she threw the ball, she was moving forward at a speed of 1.8 meters per second. And Chelsea has a mass of about 68 kilograms. And we use this as the basis for this problem. Chelsea, a 68 kilogram softball pitcher, is moving forward at 1.8 meters per second. She throws a 200-gram softball horizontally at a speed of 25 meters per second. In principle, she'll recoil. She will be moving forward less quickly after throwing the ball. How much would this throw decrease her speed? Let's take a look at the important information in this problem. Okay, Chelsea has a mass of 68 kilograms. The softball has a mass of 200 grams. Chelsea's initially moving forward at a speed of 1.8 meters per second, and she throws the ball at 25 meters per second. And what we're looking for is this. In principle, she recoils when she throws the ball. And the question is, how much would the throw decrease her speed? That's what we're trying to answer. So ultimately, the question we want to answer is this. Chelsea's initial speed, right before she throws the ball, 1.8 meters per second. Let's solve for what her final speed would be after she throws the ball. And then think about what's the change from the initial. Let's go ahead and get started. Okay, here's our initial situation. We've got Chelsea, and Chelsea is holding the softball, and the pair of them is moving forward at a speed of 1.8 meters per second. So there is some initial momentum of the system. And we want to write down what is the initial momentum. Before she throws the ball, as she's holding on to it, what is the initial momentum? How are we going to write that? We'll give you some choices. Well, since Chelsea hasn't thrown the ball yet, the initial momentum of the whole system is just equal to the mass of Chelsea, which is the mass of the pitcher, plus the mass of the ball, times the speed at which they're both moving, which is 1.8 meters per second. And we know all those numbers, so we can calculate what that'll be. The mass of the pitcher, we wrote that down, 68 kilograms. The mass of the ball was 200 grams. Well, 200 grams, we have to put that in kilograms. That's 0.2 kilograms. And that's not going to make a significant difference in the mass of the whole system. And the speed's known. And so we can calculate the initial momentum. And if we do that, we get 123 kilograms meters per second. Now, let's look at the situation after she throws the ball. After the pitch, here's the situation. Chelsea has thrown the ball. Chelsea's still moving forward, but the question is, at what speed? So let's just call that VF. That's the speed at which she continues to move forward. At this point, she's thrown the ball, and the ball is moving at a speed of 25 meters per second. Let's write down a relationship which gives us the final momentum of the whole system. What will that look like? We'll give you some choices. The final momentum is just the momentum of the pitcher, which is the mass of the pitcher times her speed, which is VF, plus the mass of the ball times its speed, which is 25 meters per second. So that's what our final momentum looks like. Now, we had an equation for the initial momentum, and we had an equation for the final momentum. And if we assume that the throw is very rapid, and the only significant forces that act are the forces that are between Chelsea and the ball, we can assume that the initial momentum is equal to the final momentum. So in principle, Chelsea will be moving less quickly after she throws the ball than before she threw the ball. So we'll make that assumption. Okay, so we'll assume that the initial momentum of the system, which was Chelsea plus the ball, is 123 kilograms meters per second. We're assuming that's equal to the final momentum. So the final momentum is also equal to 123 kilograms meters per second. But look at the final momentum. It's a combination of two different factors. There's this factor right here, which is the momentum of the ball. There's this factor right here, which is the momentum of the pitcher. And that's the piece that we're interested in, because we want to know how fast Chelsea's moving after the toss. Well, the final momentum of the ball, 0.2 kilograms times 25 meters per second, that's 5.0 kilograms meters per second. And so we solve for the final momentum of the pitcher, and that is 68 kilograms times the final speed, Vf. It's 123 kilograms meters per second of the system minus the 5 kilograms meters per second of the ball. So the final momentum of the pitcher is less. It's 118 kilograms meters. Here's what we get for our final calculation. We have 68 kilograms times Vf, and that was equal to 118 kilograms meters per second. We can solve for Vf, and if we do that, and we round off to two significant figures, we get 1.7 meters per second. She's slowed down from 1.8 meters per second to a speed of about 1.7 meters per second. She slows down by about 1/10 of a meter per second. And that's because of the momentum that she imparted to the ball. There's a change in her speed of about 0.1 meter per second because of the momentum that she imparted to the ball. And that's our final answer. Our final step, as always, is to look back at our answer and see if it makes any sense. And what we'll do is go back to the video. Let's look at the pitcher throwing the ball. She's moving forward. She throws the ball is moving forward very quickly, and you can see she doesn't slow down much. But if you do a careful frame-by-frame analysis of the video, you can see that in the instant after she's tossed the ball, she is moving more slowly than right before she tossed the ball. She slows down, in fact, from 1.8 meters per second to 1.7 meters per second, which is not a huge surprise. Physics is about the world around us.